Greetings and welcome to lecture number 18 on the course Introduction to Fourier Analysis. On the previous lecture, we defined the concept of tempered distributions. They are simply continuous linear maps on the space of Schwarz functions, equipped with the metric d. We also saw a couple of examples of tempered distributions. Every LP function defines a tempered distribution. Every polynomially bounded function defines a tempered distribution. And every finite measure defines a tempered distribution. On this lecture, we discuss a few basic operations on the space of tempered distributions, one of which is the Fourier transform. Recall that quite soon after we had introduced Schwarz functions, we observed that they are preserved by the following operations. If phi is a Schwarz function and alpha is a multi-index, then d alpha of phi is again a Schwarz function. X to the power alpha times phi is a Schwarz function. The product of phi with another Schwarz function psi is again a Schwarz function. And last but not least, the Fourier transform of phi is a Schwarz function. Back in the day, when we discussed these properties, we had not yet defined a metric on the space of Schwarz functions. Now we have the metric d, and it turns out that all of these operations listed above define continuous self-maps on the space S, D. This is the content of lemma 4.11. Let alpha be a multi-index and let psi be a fixed Schwarz function. Then the following maps are continuous maps from S, D to S, D. First, phi maps to d alpha of phi. Second, phi maps to x to the power alpha times phi. Third, phi maps to phi times psi. And fourth, phi maps to the Fourier transform of phi. The proof of lemma 4.11 is a good exercise in getting acquainted with the metric d, and for this purpose we leave most of the statements as exercises. As a model case, we just prove the first statement, which claimed that the map phi maps to d alpha of phi is continuous on the space S, D for any multi-index alpha. To see this, fix a multi-index alpha. What needs to be done is to show that if phi j is a sequence of Schwarz functions which converge to zero in the metric d, then also the alpha derivatives of phi j converge to zero in the metric d. As you may recall, convergence to zero in the metric d was equivalent to convergence to zero in every n norm separately. So what we need to do is to fix a natural number n and show that the n norms of the functions d alpha of phi j tend to zero as j tends to infinity. We do this by bounding the n norms of d alpha phi j from above by the n plus the order of alpha norm of phi j. This inequality is not hard to see. The n norm of d alpha phi j is by definition the sum over all multi-indices beta of order at most n of the L infinity norms of the functions 1 plus the norm of x to the power n times d beta of d alpha of phi j. Here, the d beta derivative of the d alpha derivative of phi j is the same thing as the d alpha plus beta derivative of phi j. Since the order of the multi-index alpha plus beta here is bounded by n plus the order of alpha, we find that the resulting expression is bounded by the n plus the order of alpha norm of phi j. This is what we claimed. Now recall that the sequence phi j tends to zero in the d metric. So in particular, the n plus the order of alpha norms of the functions phi j tend to zero as j tends to infinity. Hence, the same is true for the n norms of the functions d alpha phi j. Since the natural number n was arbitrary, it follows that the functions d alpha phi j tend to zero in the space S, D as required. This completes the proof of the first part of lemma 4.11, and as I mentioned, the other parts are left as exercises. With this lemma in hand, we can now define the same differentiation, multiplication, and Fourier transformation operations on the space of tempered distributions. This is the content of definition 4.12. Let lambda be a tempered distribution, let alpha be a multi-index, and let psi be a fixed Schwarz function. Then we define the following linear maps on the space of Schwarz functions. First, d alpha of lambda evaluated at the Schwarz function phi equals minus 1 to the power order of alpha times lambda evaluated at d alpha of phi. Second, x to the power alpha times lambda evaluated at phi equals lambda evaluated at x to the power alpha times phi. Third, psi times lambda evaluated at phi equals lambda evaluated at psi times phi. Finally, the Fourier transform of lambda evaluated at phi equals lambda evaluated at hat phi. All of the four expressions here clearly define linear maps on the space of Schwarz functions. In fact, they are tempered distributions, or in other words, continuous linear maps on the space of Schwarz functions. This statement about continuity follows immediately from the previous lemma. Let's see this, for example, for the Fourier transform. By definition, if lambda is a tempered distribution, the Fourier transform lambda hat is the linear map which takes as input a Schwarz function phi and outputs lambda evaluated at hat phi. This linear map can be expressed as the composition of two separate linear maps, namely phi maps to hat phi and the tempered distribution lambda. Both of these components are separately continuous. The Fourier transform map phi maps to hat phi is continuous by lemma 4.11, and psi maps to lambda of psi is continuous by the assumption that lambda is a tempered distribution. Hence, the composition lambda hat is also continuous, which means that lambda hat is a tempered distribution. A similar argument shows that the other three linear maps appearing in definition 4.12 are continuous on the space S, D, and hence tempered distributions. The definition of the Fourier transform of a tempered distribution should not be too difficult to memorize. Hat lambda of phi equals lambda of hat phi for all Schwarz functions phi. Since every LP function for any exponent p defines a tempered distribution by example 4.8, we are now finally in a position to define the Fourier transform of any LP function, regardless of the exponent p. Indeed, if p is an exponent between 1 and infinity, and f is an LP function, then f can be used to define the tempered distribution lambda f, namely lambda f of phi equals the integral of f times phi for all Schwarz functions phi. Now we define that the Fourier transform of f equals the tempered distribution hat lambda of f. So the Fourier transform of any LP function can be defined as a tempered distribution. This definition raises the following question. We have already given one definition for the Fourier transform of f whenever f is an LP function with exponent p between 1 and 2. Namely, by definition 4.2, the Fourier transform of such a function was defined to be a certain LQ function, where q is the dual exponent of p. Now, in definition 4.13, we stated that the Fourier transform of any LP function f is the tempered distribution hat of lambda f. Do these two definitions agree, and in which sense? First of all, an LQ function is not the same thing as a tempered distribution. So to be completely accurate, the two definitions do not agree. However, the Fourier transform hat f, which is an LQ function, gives rise to a tempered distribution lambda subscript hat f in the way which we have seen many times above. The best we can possibly hope for is that this tempered distribution agrees with the tempered distribution hat of lambda f. This is indeed the case, and this is the content of proposition 4.14. Let p be an exponent between 1 and 2, and let f be an LP function. Let hat f in LQ be the Fourier transform of f in the sense of definition 4.2. Then hat lambda of f equals lambda of hat f, in the sense that the tempered distribution on the left equals the tempered distribution on the right. The proof is very simple. It is based on the observation, which has had many incarnations on this course, that the Fourier transform of first an L1 function and then an L2 function, and in general an LP function when p is between 1 and 2, is also a weak Fourier transform. This was most recently recorded in proposition 4.3. In the current context, this proposition states that if phi is a Schwarz function, then the integral of f times hat phi equals the integral of hat f times phi. This equation is really all that is needed to prove proposition 4.14. The left-hand side here equals the value of the tempered distribution hat lambda f at phi, whereas the right-hand side equals the value of the tempered distribution lambda hat f at phi. The equation shows that these two tempered distributions agree for all Schwarz functions phi, and hence they are the same tempered distribution by definition. This completes the proof of proposition 4.14. Now we understand what the Fourier transform of a tempered distribution means, and we have seen that the definition agrees with the Fourier transform of an LP function in the sense of two equal tempered distributions. It might be a good time to mention that we could have lectured the course up to now in the opposite order. We could have started by defining tempered distributions and their Fourier transforms. Then we could have proceeded to show that if a tempered distribution is given by an LP function with exponent between 1 and 2, then its Fourier transform as a tempered distribution can be represented by an LQ function. I'm still not sure which is the conceptually clearer approach. Tempered distributions are fairly abstract, and the definition of their Fourier transform is an ingenious triviality. The definition itself carries very little information. If one wants to know anything concrete about the Fourier transforms of specific tempered distributions, for example LP functions, one still needs to do all the hard work at some point. On this course, we simply chose to do it first. Let's now return to a previous example where we were interested in finding out the Fourier transform of the function 1. This function defines a tempered distribution lambda subscript 1, and we have a definition for the Fourier transform of this tempered distribution as another tempered distribution. But now some hard work is needed in the form of the Fourier inversion theorem to find out something more concrete about this object. In proposition 4.15, we show that the Fourier transform of the tempered distribution lambda subscript 1 equals the tempered distribution lambda subscript delta 0. Here delta 0 is the Dirac measure as always, and lambda subscript delta 0 evaluated at the Schwarz function phi equals the integral of phi d delta 0. This integral equals phi at 0 by definition of the Dirac measure. To prove the proposition, fix a Schwarz function phi and start with the definition. The Fourier transform of lambda subscript 1 evaluated at phi equals the integral of hat phi times the function 1. Next, express the function 1 as e to the power 2 pi I xi dot 0. Finally, use the Fourier inversion theorem for Schwarz functions to find that this integral equals the value of phi at 0. By definition, this equals the value of the tempered distribution lambda subscript delta 0 evaluated at the function phi. This completes the proof of proposition 4.15. Many properties of the Fourier transform on the space of Schwarz functions are mirrored to properties of the Fourier transform on the space of tempered distributions. we will see just one example of this phenomenon on this lecture and then a couple more on the next few lectures. Concerning the first example, we recall the notation tilde phi. If phi is a function on Rd, tilde phi is the function on Rd defined by tilde phi at x equals phi at minus x. Theorem 4.16 states that the Fourier transform map is invertible on the space of tempered distributions. In other words, every tempered distribution can be expressed as the Fourier transform of another tempered distribution. Recall that we have seen similar statements before for the space of Schwarz functions and also the space L2. We also have the following concrete Fourier inversion formula on the space of tempered distributions. Let lambda be a tempered distribution and define the tempered distribution tilde lambda by the formula tilde lambda of phi equals lambda of tilde phi for all Schwarz functions phi. You can easily check that tilde lambda is a tempered distribution whenever lambda is. With this notation, the Fourier inversion formula for the space of tempered distributions says the following. Lambda equals the Fourier transform of the distribution tilde of the Fourier transform of lambda. You might recall that this is a perfect analogy of the Fourier inversion theorem for Schwarz functions. Of course, the whole proof of Theorem 4.16 is also based on that theorem. Recall that the Fourier inversion theorem for Schwarz functions could be stated in the single formula phi equals hat tilde hat of phi for all Schwarz functions phi. With this formula in hand, we can easily prove Theorem 4.16. Indeed, let phi be a Schwarz function and start with the definition. The Fourier transform of tilde hat lambda evaluated at phi equals, by definition, tilde hat lambda evaluated at hat phi. Next, again by definition, we move the tilde from hat lambda to hat phi. And finally, we use the definition of hat lambda. At this point, we find the expression lambda evaluated at hat tilde hat of phi, which equals lambda of phi by the Fourier inversion theorem for Schwarz functions. This chain of equations shows that hat tilde hat lambda equals lambda as required. The proof of Theorem 4.16 is complete. On the next lecture, we will see one more example of these pleasantly simple proofs where some hats and tildes need to be moved across parentheses and sometimes back again. Such a proof will yield Theorem 4.17, which states that the Fourier transform of a derivative is the Fourier transform multiplied by a polynomial. Gradually, after this theorem has been proven, we will start moving towards slightly deeper results. This concludes lecture number 18 on the course Introduction to Fourier Analysis.